In this video, we're going to talk about implicit differentiation. We are going to start by looking into what makes a function implicit and the differences with an explicit function. And then we're going to use the differentiation rules to differentiate implicit functions or to differentiate functions implicitly. So what makes a function implicit? In order to know what makes a function implicit, we should understand what means for a function to be explicit. So a function is explicit if you can identify the exact dependency on the independent variable. So for example, the function f of x equals 3x squared plus 1. This is a function that is written explicitly. I know exactly how the function f or how the function y changes as x changes. I know it's going to change in the form 3x squared plus 1. Then we are going to say a function is implicit if the way the function is depending on that variable x is not evident or if it's not explicitly stated. So for example, here we have two cases. The first one is this relation x squared plus y squared equals to 1 is an example of a case where the dependence is not explicitly stated. But in principle, we can solve this equation for y and turn it into an explicit function. However, for other relations, like this one right here, it is not going to be possible to solve for y. So it's not a relationship where we can actually see clearly what is the relationship between y and x. All we have is this equation that builds a relationship between the two variables, the independent and the dependent variable. But we don't know anything about y other than it fits this relationship. While in the first case, x squared plus y squared equals to 1, we can manipulate this and get to the evident explicit expression of y equals plus or minus the square root of 1 minus x squared. So the question is now, how do we differentiate a function that I don't know? And the answer is we need to use the differentiation rules, and especially we need to use chain rule to determine the derivative of the whole expression. So let's consider the example that we had before, x squared plus y squared equals to 1, and say we wanted to find the derivative of y. The derivative of y is going to be y dash, right? This is what we want to find. So in order to get y dash, we need to differentiate this relationship completely, entirely, left hand side and right hand side at the same time. So the thing that you want to do is to do the derivative with respect to x of x squared plus y squared, and that is equal to the derivative with respect to x of 1. 1 is a constant, so we know the right hand side is going to be 0. And the left hand side, you can separate the derivatives because it's a sum. So this would be derivative with respect to x of x squared plus the derivative with respect to x of y squared. And these two expressions, you would use the power rule to differentiate them. So 2x would be the derivative of x squared, and the derivative of y squared would be 2y, but this is a composition. This is the composition of the function x squared and y. Therefore, we need to multiply by the derivative of the inside function, which in this case is y. So we multiply by y dash using chain rule. And this we get is equal to 0. So if we're interested in finding the first derivative, then what we have to do now at this point is to solve this equation for y dash. So this way we know that y dash is going to be equal to minus 2x divided by 2y, or y dash is equal to x over y negative. This would be the final answer for that. Let's consider another example. X times y power 3 equals to 2x plus 1. And again, we want to find the derivative of y using this expression. Similar to what we did before, we're going to start by differentiating left hand side and right hand side at the same time. So you want to do the derivative with respect to x of x y power 3 equals to the derivative with respect to x of 2x plus 1. Now you want to use the product rule on the right hand side. Don't forget y is a function of x, so this would be the product of two different functions of x, so we need to use product rule. So derivative with respect to x of x times y power 3 plus x times the derivative with respect to x of y power 3. And then in the right hand side, we just differentiate to x plus 1 normally, and the derivative of that is 2. Now on the left hand side, the derivative of x with respect to x is 1 times y power 3 plus x, and the derivative of y power 3, we need to use chain rule and power rule, because the derivative of y power 3 is going to be 3y squared, but because of chain rule, we multiply by y dash, and that is equal to 2. And now if we want to find the derivative, we just need to solve this equation for y dash. So y dash is equal to 2 minus y power 3 divided by x times 3y squared. Unfortunately, because we don't know anything about the y in this particular question, the derivative of y dash is dependent on the values of x and the values of y. Let's do one more example. This time we're including a function that is not as trivial as a polynomial. So we have here an exponential function. To differentiate this implicitly, you want to do the derivative on both sides like we did before. Please notice that in this case the y is also in the exponent of the expression. That's going to be very important. And because this is an exponential function, you know that you will have to use chain rule because the exponent is a function. On top of that, the level of difficulty here is a little bit higher because the exponent is a product of two functions of x. So the exponent is the function x and it's the function y squared in a product. So apart from using chain rule, I need to use the product rule as well in a different order than I did it in the previous example. So to do that, I'm going to remember that the derivative of the exponential should be the same exponential. So the derivative should be e to the power of x y squared. But now I need to multiply by the derivative of the exponent. And this is because of chain rule. And the derivative of the exponent should be the derivative of x times y squared. And then on the right hand side we have 3x. The derivative of that is simply 3. Now I'm going to work on the derivative of x times y squared, and that is going to be very, very similar to the derivative that we did in the previous example. So for that we're going to use the product rule, and we're also going to use chain rule again. So I'm just going to keep e to the power of x y squared right there, and I'm going to work with this expression separately. So derivative of x times y squared plus x times derivative of y squared, and then this should be equal to 3. Now this is equal to e power x y squared. Derivative of x we said is 1 times y squared plus x times derivative of y power 2 is going to be 2y y dash, 2y from the power rule times y dash because of chain rule, and then this is equal to 3. So if I wanted to solve for y dash in this expression, I need to first divide e to the power of x y squared to the other side. So this becomes y squared plus 2xy y dash equals to 3 e to the power of minus x y squared. Because it's dividing now, it takes a negative value in the exponent. And then I just solve for y as I would normally. So this is 3 e to the power of minus x y squared minus y squared, everything over 2xy. And this will be the final answer. As you can see again, the dependency on x and y, the implicit nature, is carried over to the derivative as well.